Hello everyone. This is Chi Jiaming, your instructor for the Deep Learning course. Let's get started with our lesson now. Hello everyone. Welcome back to our Deep Learning course. Today, we're continuing with Chapter 2, Neural Network Foundation 2. I'm still your lecturer, Chi Jiaming. Let's dive into one core topics today, the training process of neural networks. First, we enter Part 2.3, Training of Neural Networks. Training is the key to making a neural network learn from data, so let's break down its steps and core algorithms one by one. The training process of a neural network follows a clear cycle, with 6 main steps. First, parameter initialization. Use methods like constant initialization, normal distribution initialization, or uniform distribution initialization to set initial parameter values. Second, batch data splitting. Instead of using all data per training round, select a subset called a batch as input. Third, forward propagation. We'll detail this next. Fourth, establish loss function to measure prediction error. Fifth, backpropagation to update parameters. Sixth, check iteration count. If the number of iterations is reached, end training. If not, repeat the cycle. The flowchart on the slide clearly shows this loop. Forward propagation refers to the forward calculation process of a neural network. To run it, you need 3 things: the network's input data, its connection structure, and the parameters, weights or biases, of each neuron. Take the 2-layer fully connected neural network in the figure as an example. Data flows from the input layer, through the hidden layer, after weight summation and activation, and finally to the output layer. The formulas on the slide, like A subscript 1 equals the sum over I of W subscript 1 subscript I times X subscript I, plus B subscript 1. Show how each layer transforms the input step by step. The loss function quantifies the error between the model's predicted value and the real value. The slide shows a common one, mean squared error, MSE, calculated as MSE 1 over n times the sum from I equals 1 to n of the quantity y sub I minus y minus hat sub I squared. Let's clarify the parameters. First, Y is the real value of the ith sample. Second, Y is the predicted value of the ith sample. Third, N is the total number of samples. The smaller the MSE, the better the model's prediction performance. Gradient descent is the core algorithm for updating network parameters to minimize loss. Its foundation is using derivatives to find the direction of parameter adjustment. The slide uses the function f theta equals theta squared as an example. Its derivative f theta equals 2 theta. The graph shows that when theta is positive, the derivative is positive. We need to decrease theta. When theta is negative, the derivative is negative. We need to increase theta. This is how gradient descent finds the minimum of the loss function. The core formula of gradient descent is theta equals theta minus alpha, f theta, where alpha is the learning rate, controls step size. For neural network parameters, weights W are updated as W equals W minus alpha, dW is the gradient of loss with respect to W. Biases B are updated as B equals B minus alpha, dB is the gradient of loss with respect to B. This formula ensures we adjust parameters in the direction that reduces loss. There are 2 common variants of gradient descent. First, mini-batch gradient descent (MBGD). Split all samples into small batches, then run gradient descent on each batch to update parameters. Second, stochastic gradient descent (Singapore dollars). Use only 1 sample per batch to update parameters. It's more flexible, but has severe oscillation and low efficiency. As the figure shows, both MBGD and Singapore dollars oscillate during loss reduction, Singapore dollars more so. The batch size is chosen based on actual task needs. To fix oscillation and speed up convergence, we have improved algorithms. First, gradient descent with momentum. It accumulates past gradients using parameter beta to smooth updates. The formula is VDW equals beta, VDW plus 1 minus beta dW, then W equals W minus alpha, write VDW, same for dB. Second, Rumsprop algorithm, it uses the moving average of squared gradients to adjust step size, making updates more stable. Both algorithms reduce oscillation compared to basic gradient descent. Another powerful improved algorithm is adaptive moment estimation, ATOM, which combines the advantages of momentum and Rumsprop. Its key formulas include accumulating first-order moments, VDW, and second-order moments, SDW, then correcting them for parameter updates. ATOM has clear advantages. It uses less memory for the same data size, has relatively fixed hyperparameters, works well for large-scale training data, and is tolerant to sparse gradients and gradient noise, making it widely used in practice. Backpropagation is the process of calculating gradients from the output layer back to the input layer, reverse of forward propagation, to update parameters. Let's use the three-layer network, input hidden, output in, the figure. Forward propagation steps, z subscript 1 equals w subscript 1 times x plus b subscript 1 equals sigma, z, sigma is activation function, z subscript 2 equals w subscript 2 times a subscript 1 plus b subscript 2 is output. Backpropagation uses a, output, and the loss function to calculate gradients of w, b, laying the foundation for parameter updates. Let's extend the backpropagation example. First, complete forward propagation as we did earlier, xz, az. Second, define the loss function. The slide uses cross entropy loss. E total equals minus y log a minus 1 minus y log 1 minus a. Y is real label. Third, in backpropagation, calculate the total error, E total. Update weights from hidden layer to output layer, W, using the error gradient. Update weights from input layer to hidden layer, W, by propagating the error back to the hidden layer. This reverse calculation ensures all parameters are adjusted to reduce loss.